about some recent work that's been being put out lately on quantum and classical algorithms for topological data analysis. So topological data analysis, the whole point of this topological data analysis is to use algebraic topology or tools from algebraic topology, specifically what's called singular homology, to study the topological properties of a data set. And specifically what you're interested in are the holes that are there in your data set or that are associated with your data set. And the reason people wanted to apply these tools to data analysis is because instead of just revealing information like connectivity between clusters of data points, it also reveals some higher dimensional structures that may be physically relevant depending on how the data was sampled or where it was sampled from and so on. But personally, though, I think rather than this TDA, as I will abbreviate it, rather than TDA having some super killer application that it is uniquely well suited for, I think some of the most interesting aspects of this problem are complexity theoretic, and I'll get into that later towards the end of the talk. But in terms of applications, I've seen it applied to analyzing filament structures between within galaxy clusters, breast tumor detection, and multi-qubit entanglement. If you're interested in some of the applications people have developed for this. So the question is, okay, I mentioned you want to extract holes from your data set. So how do you do this? And the way people do this is what's called persistence homology. So before I get into that, I have to discuss, okay, what is homology? And before I do that, I have to talk about a bunch of other things to start off with. So first, I need to talk about what is a simplex. And a simplex, for those of you who don't know, is basically, okay, so let me go from left to right on in this image. So you have a point here. This is called a zero simplex. You have and then this thing to the right, you have 2 points and a line connecting them or an edge connecting them. That's a one simplex. This filled in triangle, it's a two simplex, and this tetrahedron over here is a three simplex. So basically, you can think of it as a convex hull of a collection of points. So crudely, loosely speaking, and the reason that, for instance, this is called a one simplex rather than if you might be inclined to call this a two simplex is that you want to consider the dimensionality of this object. So this is a one-dimensional object, so which is why it's called a one simplex, even though it has 2 points, and then so on for the rest of the objects. So then now that you have these simplices, you want to use them as building blocks of what are called simplicial complexes, which are basically, again, loosely speaking, ignoring some technicalities here, collections of simplices that are glued together in some nice ways. But they have to be glued together in certain ways. So for instance, if you look at this image over here, you'll see that this simplicial complex, these two simplices are glued along this edge, these two simplices are glued on the common vertex, and so on. And so this is one of the conditions for how you define a simplicial complex. They have to intersect, if they intersect at all, on a common boundary. So for instance, in this object over here, this would not be a valid simplicial complex because these two simplices, two simplices, they intersect somewhere in the middle over here, and that this would not be a boundary of either of these simplices here. So you would not call that a simplicial complex. So okay, you might be wondering, given a point cloud, because if you have just a data set that's just a point cloud, how do I create a simplicial complex out of that? So what you do is, let's say you pick an epsilon, and this choice of epsilon will be motivated by how or the physics or the physicality of your data set. So namely the context the data set was extracted from. But anyway, from a mathematical perspective, let's say you pick an epsilon, and then imagine, if you will, drawing epsilon balls around each of these points. So you basically have a cover. And then what you do is you can draw a simplicial complex based on how these epsilon balls intersect. So what I have over here is a simplicial complex called a check complex. That's CECH. And that's what the C over here means. And the epsilon subscript just means that it's at a scale epsilon. So the way you determine the simplicities of the simplicial complex is you look at, let's say look at these three vertices. So this vertex, this vertex, this vertex, and you basically look at if all of these mutually intersect. So if you look, it may be a little hard to tell here, especially with this laser pointer, but if you look around here, there's a white gap in the middle, which means that they do not all mutually intersect. So you would basically not fill in this simplex, this two simplex over here, determined by these 3 points. However, if you wanted to determine the one simplicities of this simplicial complex, all you need to do is look at the pairwise intersections. And then, so for instance, for these 3 points, these two intersect, these two intersect, and these two intersect. So you would still draw like edges between each of them. So you would have a hollowed out 2 simplex for the simplicial for these 3 vertices. So more generally, for any K simplex, you would look at if all the K plus 1 points that make up that K simplex have mutually overlapping epsilon neighborhoods. And if they do, you draw a K simplex. If they don't, you don't. However, as you might, some of you might be able to intuit, this is very difficult to determine, or computationally intractable to determine for large data sets, because it requires you to take very large number of data points to determine if they all mutually intersect. And that's computationally intractable. So what instead people do is they construct what's called a RIPS complex, R for RIPS, RIPS. And the main difference between this check complex and this RIP complex is that if you again look at these 3 points, you would in fact draw 2 simplex if they pairwise intersect. If all the pair points within this collection of 3 vertices pairwise intersect. So for instance, as I pointed out before, these two intersect, these two neighborhoods intersect, these two neighborhoods intersect, and these two neighborhoods intersect. So you would just say, okay, there probably is a hole there, and then you would actually fill that up and draw a 2 simplex. Is there any questions so far about any of this stuff? Okay, cool. So, oh yeah, sorry.
Go ahead, Abishek. I think you are fine.
Okay, cool. Right, so that's the main difference between a check complex and a RIPS complex. Now, one thing to note is that you have this cover here, consisting of a whole bunch of neighborhoods. And the question is, okay, like I have these, from them I've abstracted the simplicial complex. So what's the guarantee that they represent the same topological information? And the answer is that they don't, because for instance, in this check complex over here, there are 3 holes. There are 3 voids in here, whereas in this RIPS complex, there's only 1. So they don't in fact represent the same topological information. And in fact, there's a theorem that says that it's actually the check complex that represents the topology of this cover over here, whereas the RIPS complex does not. So this you might think causes a problem, because okay, so the check complex is computationally intractable to determine, so are we basically just dead in the water? And the answer is no. The trick is what you do is you consider some notion of persistence. So let me explain how that works. So let's say I've sampled a bunch of points from a torus as depicted here, and I again pick some starting value of epsilon. I draw epsilon balls, and I determine a RIPS complex from them based on how these epsilon balls pairwise intersect. And then what I do is I increase the scale, or increase the epsilon, which means I'm increasing the size of these epsilon neighborhoods on each of these points. And then they do the same thing. I determine the simplicial complex associated to this cover, the RIPS complex associated to this cover, and I keep track of the number of holes. And the number of holes, by the way, are what's called the Betty numbers of this simplicial complex. So the Betty number basically tells you how many there's n of them going from 0 to the dimension of the simplicial complex, which is basically the dimension of the largest simplex in that simplicial complex. And they basically tell you how many holes there are of those dimensions. So for instance, in this simplicial complex, there's 2 one-dimensional holes. So you would say that has a Betty number of 2, the first Betty number of 2 rather. And then this Betty number here has a first Betty number of 3 for the simplicial complex. So basically you keep determining these simplicial complexes, and you keep track of like what Betty numbers there are. And you basically keep increasing them, the size of your neighborhoods. You do the same procedure. And you can kind of start seeing that as you increase the neighborhoods, the size of the neighborhoods, you start off with a bunch of points, but then you start filling in edges, and you start filling in higher dimensional features, and then eventually at some point they become too large, and you start plugging in all the holes in your simplicial complex, and at some point all you're just left with is some giant blob, which right. So the question is, okay, how do I then know, how do I extract like something topological about this data set? Because I have a whole bunch of discrete, simplicial complexes at different points in of my parameter space that's determined by epsilon. And the question is, what do you do? And the idea is, what you do is you plot these Betty numbers for these RIPS complexes. And you basically look at the length. So over here on the x-axis is basically the parameter, like the range of epsilon that you chose to dolly like your simplicial complexes over. So basically, think of these as like a parameterized family of simplicial complexes where the parameter is epsilon. And then on the vertical axis, what you have is the generators of your homology groups, which are basically which again basically tell you the dimension of the homology equals basically tells you the number of poles. So they basically tell you the Betty numbers of your simplicial complex. So for instance, if you look at this image, this third image over here, basically if you were to draw a dashed line from this image down to these, barcodes as they're called, because they look like barcodes, you basically look at how many bars it intersects. So for instance, I told you that there's in the previous slide that there's 3 holes in the simplicial complex, and then it intersects these 3 bars of this first homology group. So that tells you that there's 3 holes in this 3 one-dimensional holes in this data set. And the length of the bar basically tells you for how long the feature persists. And there's a theorem that says that if you have a RIPS complex at some scale epsilon, and let's say it's a scale epsilon over epsilon root 2, then the check complex at scale epsilon sits somewhere in between. So basically, the implication is that any topological feature that persists under under like a RIPS complex at scale epsilon and a RIPS complex at scale epsilon root 2 times root 2, then that means that's like an intrinsic topological feature of your data set. Whereas if you had a feature that appeared and then disappeared shortly thereafter at these different scales of epsilon, then that tells you that's not like an intrinsic feature of your data set. So for instance, this bar is very long. That tells you that there's probably something there, like a actually meaningful hole there. This bar is very long, so that tells you that there's something intrinsic to the data set there, and so on. And so just to be clear, if you look at this this cluster of points over here, the reason why this is important is at least in this low dimensional example is that, for instance, this hole, it persists here, here, and here, and it only really gets filled up around here. So what this is telling you is that there's really some gap between these points for whatever reason at these 3 scales. So that's the kind of information you can detect. And again, this extends to higher dimensions. So that's basically it. And again, I'm just before I move on to the next part of the talk, I just want to ask if there's any questions about some of these preliminaries.
Yeah, we'll pause for a sec, Abishek. Are there any questions in the audience at this point? So I guess I do have one question. So there is sort of these 2 notions of how you can form these simplicial complexes, and one is easier, but it's still related to the one that actually contains the topological information. Is that right?
That's right. So as I was saying, if you have these RIPS complexes, as they're called, at some scale epsilon, and then you have another one at scale epsilon over 2, then there's a theorem that says that the check complex, which is the thing that actually contains your intrinsic topological information, sits somewhere in between those 2. So you can basically approximate the thing that actually represents the topological features of your data set by these more coarse-grained simplicial complexes. And that's why you basically use this parameterized family of these RIPS complexes, because and then you look at which ones persist, which topological features persist, because then that actually captures like what's actually there, like what's actually intrinsically there in your data set. Does that answer your question?
Yes, yeah, it does. Thank you. Other questions? Okay, Abishek, I think we're all good to go on. So I'll just interrupt you again if there's another question.
Cool. So so this has all been done and known classically for a decade or 2 decades or so. But then interest in the quantum realm started when Seth Lloyd at MIT proposed a quantum algorithm for doing this exact procedure that I mentioned over here previously. And he claimed at the time an exponential speed up on for doing this process on quantum computers compared to the best classical algorithms. So before I get into like the validity of those claims, I just wanted to talk about what the algorithm that he proposed was. So the idea, well, first of all, the claim is that he could find the eigenvectors and eigenvalues of what's called this combinatorial Laplacian, which I'll talk about in a minute. And basically the idea is these eigenvectors and eigenvalues of this matrix, you can use them to determine the Betti numbers of your simplicial complexes. And you claim to be able to estimate all the Betti numbers up to all the Betti numbers of your simplicial complexes in time that's n squared over delta. N is the number of data points that you have in your data set, and delta is the multiplicative accuracy to which you want to determine the Betti numbers. And in the proposed speedup claims from diagonalizing a 2 to the n by 2 to the n sparse matrix, which takes time order n squared on a quantum computer, but order 2 to the 2n on a classical computer. And there is a big asterisk next to this claim, which I will get into in a minute, but this is at least what the claim was at the time when he published this in 2016. So okay, how did he go about doing? What was the quantum algorithm? So the idea is first, so these K simplices, what you do is you have you basically order the vertices in the K simplex in some ascending order. And you basically then identify a K simplex with an n-bit string but locate with ones in the locations where the vertices actually exist. So let's say you have n data points, then you have an n-qubit string, and then a K simplex in that data set. You would basically mark a 1 in the positions where the data set exists with respect to some ordering of the vertices. So you basically have like some bit string with ones and zeros. And then the simplex is basically just a state in some n-qubit quantum state in some c to the 2 to the n dimensional vector space. And then so the idea is given n data points, you basically do the same thing. You fix a parameter at a starting value to determine the Ripple complex based on how closely the points are together, whether or not they basically lie within epsilon distance or 2 epsilon distance from each other. Then there are two relevant notions of subspaces over here. Now, given n data points, the number of possible possible K simplices that you can form, given n data points, is n choose K plus 1, because the K simplex has K plus 1 data points, and there's precisely n choose K plus 1 ways of choosing or forming K simplices. But in a given data set, only like a fraction of those that actually exist or that can exist are actually there in your data set. And so this larger space of all simplicial complexes is called WK, W sub K. And then the subspace that we're actually interested in is what we're calling H sub K. And then the superscript epsilon, just in case that this is at a particular scale epsilon that we've chosen. So the full simplex space at K scale epsilon is this direct sum of these vector spaces. So you have like starting from your 0 simplices up to your n simplex, if there are any. You basically have like a direct sum of all these vector spaces. And now you need a quantum algorithm for evaluating the distances between pairs of points. So this is equivalent to applying a projector. Basically evaluating a projector onto the physical subspace, this H sub K subspace from the larger subspace. And there's a cost associated with doing this, which I will mention in a minute. Then the idea is you can construct a uniform superposition of these simplex states using Grover's algorithm, and basically the state preparation will reveal the K simplices at some particular scale epsilon in this amount of time, which depends on the square of your number of data points, and then depends on this accuracy, which we're calling like C. C sub K rather. And this is basically just precisely the ratio of the K simplex, the dimension of your K simplex space, to the dimension of the overall space of possible simplices. And then so then independently what you do is you define what's called a boundary map, which I've so you define a boundary map. And basically what this boundary map is doing is it acts on a K simplex state, this vector, and it basically gives you some linear combination of vectors that are one-dimensional, that represent simplices of one lower dimension. So here's a physical example of what I mean. Let's say you take this simplicial complex over here. So this boundary map, and what it's physically doing is it's basically taking this entire two-dimensional simplicial complex, and it's giving you this linear combination of the edges that are on the boundary. So it's literally just giving you the boundary of this two-dimensional simplicial complex. So that's how you should think of this, and the plus or minus signs are basically giving you like an orientation. So for instance, in this case, the orientation is this way, and that's what it would give you. Now, associated with this, these boundary maps are what are called cycles and boundaries. So a cycle is basically a simplex such that the boundary map, when you apply the boundary map to that simplex, this cycle, you get 0. So this is an example of a one cycle. It's called a one cycle because it's one dimensional. And so basically the idea is if you, and the one cycle over here is basically these edges that are on the boundary over here, and they're marked by these arrows. And the idea is if you were to apply the boundary operator to the simplices that are on these edges, that are on the exterior here, you would get 0. And the reason being that if you, let's say, look at this simplex over here, this edge, if you were to compute the boundary of this, you would get these two vertices that are on the boundary of this one simplex. So you get some point over here with some sign, and some point over here with some sign. But the idea is that each simplex, each zero-dimensional simplex over here, that's on the boundary of this one simplex, is also in the boundary of another simplex. So this point over here is on the boundary of this edge and this edge. So, and they come in with opposite signs. So if you were to do the sum, you basically get 0. You basically get some cancellations, and then they all cancel out pairwise, and then you get 0. So that would be a cycle. Now, what's a boundary? A boundary is a simplex such that it is a boundary of a higher dimensional simplex, namely a simplex one dimension higher. So for instance, this over here is called the one boundary, or like the edges over here on the exterior of this two-dimensional simplicial complex is called a boundary because it is in fact the boundary of a higher dimensional simplicial complex. So that's why it's called a one boundary. And in this case, and the thing to note is that these cycles are in fact the kernel of the boundary map, and then the boundaries are the image of this boundary map. So they're basically two subspaces that are associated to your space of K simplices. And you can also show that if you apply the boundary operator twice, like let's say the boundary operator acting on K plus one dimensional simplices, and the boundary operator acting on K dimensional simplices, and you compose them, you get 0. So what this tells you is that the image of this K plus one dimensional boundary operator is contained in the kernel of this K dimensional boundary operator. So basically, it tells you that the space of boundaries is contained in the kernel of the partial K operator. And then for the purpose of this algorithm, you also want to define these modified boundary operators, which apply the projector first. So you actually project onto the physical space that contains the simplices that are actually there in your data set before applying the boundary operator. And by the way, this is basically, if you were to pick a basis of your vector space and write the matrix elements of the boundary operator, this would be a sparse matrix. So you can basically just think of this as a matrix acting on vectors. And then what you do is basically then form this quotient vector space, which is basically the kernel of this partial K operator over the image of the partial K plus one operator. And this is called the K homology group. And the dimension of this vector space, this quotient vector space over here, is essentially the Betty number. And it basically tells you, the cycles that are not boundaries. So for instance, this is a cycle that's not a boundary of a higher dimensional simplex because this is basically enclosing a void. There's no like higher dimensional simplex that it is a boundary of. And this hole over here is sort of representing that fact. So this is basically representing the holes in your data set. Now, for the purpose of this algorithm, what you want to do is, since this is not—
Hey, Abishek, can I interrupt you real quick?
Yeah.
So I had a question about the modified boundary operators. So can you explain why we want to project onto the K simplex subspace first and then apply this boundary operator? Is the boundary operator for K still defined?
Yeah, absolutely. Yeah. So the reason is, so you don't want to act on so there's a vector space of all the possible K simplices you can construct from a data set of n points, and which is that of dimension n choose K plus one. But the simplices that are actually there in your data set, the simplices that you've actually constructed based on a particular scale, epsilon, those are only going to be a small portion of that. Does that make sense?
Yeah, it does. And sorry, I just have one more question. So it sounds like you're saying that the things that are holes in our complex are cycles that aren't boundaries. So I see why a
Yes.
hole would be a cycle, but maybe I just don't see off the top of my head why it's important that these holes are not boundaries. Do you think you could shed some light on that?
Right, because if it's a boundary, then that means there exists. You can think of it as in the interior of this boundary. Loosely speaking, there exists a higher dimensional simplex that it is a boundary of. So for in this image, for instance, it is not actually bounding anything that's higher dimension. They basically just a void there.
I see. It's filled, so it's not a hole. Because
Right.
just to say it, kind of really
Exactly.
elementary. Okay, gotcha. Thank you.
Yeah.
Any other questions?
Thank you for asking that, because that's the more intuitive way of phrasing it.
Awesome. Cool. Okay. Yeah, I think we're good to go on.
Right.
Thank you.
So, right. So you have this boundary operator, which is just basically a sparse matrix. Now the one issue with it is that it's not a Hermitian operator, because it's an n choose k times n choose k plus 1 matrix. So what you can do, the trick here is then you can embed it into a Hermitian operator, which is basically you embed it into this block, this off diagonals of this this larger matrix. So on this part of the diagonal, you have this partial k, and then you have its adjoint on the other off diagonal element. And this would be an operator that acts on the direct sum of this k minus 1 simplex space, and with the vector space of k simplices that are actually there at a scale epsilon. And so you can basically take the direct sum of all these. So you get basically that like this off diagonal structure. And you have like this nice pattern over here repeating all the way down. And I'm going to call this B superscript epsilon with no subscript, because this is basically the direct sum of all these individual boundary operators acting on the on like the 1 simplex space, the 2 simplex space, and so on. And then what you can basically do is you can take this square, you can just basically apply it, you can multiply it by itself, see what you get, and you basically get this nice diagonal structure. And the individual operators that are on these diagonals are what's called the combinatorial Laplacians. And so basically you can think of this B operator that I started with as something like a Dirac operator, because you can think of it as a square root of the Laplacian. And so there's an analogy here with QED for those of you who've done QED. But anyway, you call these operators the Laplacians, so they act directly on the space of k simplices. And again, I should mention that this adjoint is acting on it kind of goes in the other direction. So the boundary operator, let's say the partial k belt plus 1 boundary operator, acts on k's and k plus 1 simplices and returns a k simplex. The adjoint is the reverse; it acts on k simplices and gives you a k plus 1 simplex. But you can check that you can, as a sanity check, you can just check and see that this actually in fact acts on k simplices. So why do we care about this object? And there's a theorem there's basically an entire theory called Hodge theory in differential geometry, which basically says that the Betty numbers, the homology groups, the dimensions of the homology groups, you can actually get from looking at the kernel of this operator. And there's a discrete version of that, which is adapted to our discretized case where we're considering not just manifolds, but simplicial complexes. And it's the same exact thing. Basically, the Betty number is essentially the dimension of the kernel of this Laplacian. So if you want the kth Betty number, the number of k-dimensional holes, then you basically look at the kth combinatorial Laplacian, you look at the dimension of its kernel, and then you can extract that information. So basically, this boils down to like a rank estimation or a kernel estimation problem, whichever way you want to see it. So, okay, how do you extract the eigenvalues and eigenvectors in this object? The idea is you have your uniform superposition of k simplices that we constructed, a couple slides back, and then over here, what you can also do if you want to is take a uniform superposition of those or all the scales, but you can also just consider a particular scale. Either way, it doesn't matter. And you can essentially use phase estimation to decompose that into the eigenvectors of this boundary operator to to get the eigenvalues and eigenvectors. And the probability of getting an eigenvalue is actually proportional to the dimension of the eigenspace. Now, doing this, getting the eigenvalues and eigenvectors on a classical level, if you were to use something like Gaussian elimination to diagonalize everything and then get the rank of that matrix, this would take order something like 2 to the 2n, or again, n is a number of data points. However, phase estimation, this whole procedure takes n to the 5th over delta times this, square root of epsilon, which again is the accuracy to which you want to construct the simplex state. And this is determined by the ratio of the simplices that are there in your simplicial complex at a particular scale over the all possible case simplices. The extra factor, so the phase estimation part actually takes n cubed over delta, and n squared takes an additional time. And the n squared is because it takes a time order k squared to evaluate the projectors onto your physical subspaces. So that's basically the cost of that algorithm. And and you can also use this to identify the dimension of the eigenspaces in time, which scales like this, where this eta L parameter is basically the dimension of the alpha eigenspace over the space of k simplices. There are a few caveats to this algorithm. This algorithm really estimates the number of low-lying states, not the exact Betty numbers. So these are basically the normalized Betty numbers within a certain small range of eigenvalues. But the interest that the reason that it attracted this whole algorithm attracted a lot of interest is because it has resisted dequantization. So around the time this was published, there are a lot of results on dequantizing, algorithms that were initially claimed to have exponential speedups, and this for many years was resisting dequantization. So that's why this whole procedure attracted a lot of interest. So this raises two questions: one, are there randomized classical algorithms, and two, is the speedup actually exponential compared to classical algorithms? So I'll pause here again and ask if there are any questions before I move on to the next part.
Can I ask a quick question?
Yes.
So far it looks like basically what this algorithm is doing is computing the Betty numbers, which is not, it's strictly less information than the full persistence diagram. So does it ever go as far as figuring out the actual persistence information?
Yeah, so then if you want to do so that's where these boundary operators at the scale, so like B superscript E comes in, because this is a direct sum of oh, okay, I see your point. You can also basically extend this to incorporate all your scales that you want to consider. So you can create an even larger matrix, and then do phase estimation on that and get that information. Or you can just take this entire procedure, run it repeatedly, and in each step you tabulate your Betty numbers.
Thank you.
Yeah. So does that answer your question?
Yeah. Thanks.
Yeah, and actually, and in their paper, I think in their footnotes in this Lloyd paper, they do consider what if you want to simultaneously consider the matrix on every possible scale and on all possible simplices. So this would just be an even larger matrix. Yeah.
Okay, Abishek, we have a question in the audience. Do you want to go ahead and just try to say it, and maybe we'll see if.
So this is only about like finding the Betty numbers after having the sequences. So it's not related with how to find the sequences in the numbers like in X, like we didn't do the balls and everything. It's not optimizing that. He already got the sequence in the X node step, and then he did without the Betty number, right?
Did you pick that question up, Abishek?
I did not. Can you repeat it to me?
Okay, yeah, I'll try. So I think it sounds like, I think the question concerns which parts are we doing in the quantum algorithm? Do we assume we already have some representation of the simplicial complex for the data in this algorithm? Or are we just taking that as a given input and then working with it thereafter? Does that make sense?
Yeah, so the parts of this algorithm that are quantum are, so let me go back. Yeah, so I acknowledge this might have been confusing because I was mixing topology and like in the actual parts of the algorithm. So the parts of the algorithm that are quantum are evaluating the projector onto the physical simplex space. The part where you use Grover's algorithm to construct this linear combination of simplex states. And as far as the input to the algorithm is concerned, you're just being input the number of data points. Yeah, you assume that you have a projector that can evaluate the distances between those points, because you only need information about the pairwise distances between points to determine if you have a K simplex. and again, we're considering mainly constructing RIPS complexes here, not check complexes. So you only need that information. And that's why you have an additional cost of n squared if you want to evaluate that projector. And then, of course, then you use phase estimation at the end, and that's the other quantum part. Oh, did that answer the question?
Yeah, it sounds like the question asker is satisfied. Are there any other questions? Okay, I think we're good to go on. Thanks, Abishek.
Right. So the questions. So once this algorithm came out, there was a lot of skepticism that they were not really comparing to the right type of classical algorithm. And I mentioned over here, is there a randomized classical algorithm? Because Gaussian elimination is like a sort of a deterministic algorithm. It's a very brute force algorithm where you diagonalize a large matrix. And the question is, if you come up with a randomized classical algorithm, that would actually be a much more valid comparison to make between the quantum algorithm proposed here and some classical algorithm like Gaussian elimination. So this is where my advisor and I, we worked for the past couple of months to develop a path integral Monte Carlo algorithm for doing this topological data analysis. So the idea is working with the same exact objects that they worked with that I discussed in the previous portion of the presentation. The idea is you want to use imaginary time evolution to create a projector onto the kernel of this combinatorial Laplacian. And I should also preface this entire portion of the talk by saying that what I'm assuming is that we're given a graph as an input, and the graph basically tells you the information about which vertices are connected. So we're not assuming that we're given an input as a number of data, as like the data points. What we're being input is the graph, and we have an oracle that we can query that tells us whether or not vertices are connected or not. And we can use that information to determine if we have a K-simplex or not. So more specifically to create this projector, we want to work with the square of the Dirac operator. The Dirac operator being this, and this square of this operator is precisely the combinatorial Laplacian. And then, so what we do instead is we don't just want to consider the square of this operator. We basically add this energy penalty term, which is basically which basically ensures that you project onto the space of simplices that are actually, or the simplices that are actually there in your simplicial complex. And gamma min over here is basically the spectral gap of the combinatorial Laplacian. It's basically the second smallest, upper bounded by the second smallest, the first non-zero eigenvalue, because you will generically have like a bunch of zero eigenvalues as well. So you basically slightly modify this Laplacian by adding this penalty. And I'm going to call it coefficient sine theta. Sorry,
I hate to interrupt you. So, I think our university's been having some interesting internet issues. Would you mind going back? I think you were talking about the energy penalty term, the gamma min. Yeah, we sort of cut out after that. Would you mind just starting there again? I'm so sorry to interrupt.
Oh yeah, no worries. So all I was saying was that you still want to work with these, the square of this operator for this algorithm. But you slightly modify it by adding this additional term, which creates a projector onto the simplicities that are actually there in your data set. And then this gamma min factor over here is basically the spectral gap of this operator, this Dirac operator, or the Laplacian rather. And so that's all that was. And then what I was saying was that if you have given a vector in some vector space, you can decompose it as a linear combination of a vector that's in the kernel of the Laplacian and something that's in the orthogonal complement of the Laplacian, and you call the coefficient sine theta cosine theta. And then if you evaluate the expectation value, so you evaluate the expectation value of e to the minus t times this modified Laplacian. And this is basically bounded by cosine squared theta plus sine squared theta, and then e to the minus gamma min t. T over here is like the time evolution. the time evolution parameter. And so the idea is if you pick t greater than log 1 over epsilon over gamma min, epsilon being the error, then the expectation value will be at most cosine squared theta. So the idea is if you pick these vectors as columns of a Haar-random unitary, and you basically take an average over all these cosine squared theta values that you basically get an answer that's the dimension of the kernel of this combinatorial Laplacian over the dimension of the entire K simplex space, which is basically what these two numbers beta k and dk mean. So then what you do is you have this Laplacian and you basically decompose it in terms of one-sparse as a linear combination of one-sparse matrices. And there's various theorems that are out there that tell you that this can be efficiently done classically. And D over here is some upper bound, which depends on the K, K being like the K that's appearing over here, this is in the subscript. And it also depends on the degree, the maximum degree of your vertex in your simplicial complex. And then what you can do is we can basically just do trotterize. You basically trotterize this, and we use a symmetric trotter formula. So you have 2 times R times D terms in the symmetric trotter formula. And then this is the error scaling. And then what you can do is, as you always do in physics, you basically can insert resolution of identities in between each of these terms. And basically you're expanding each term in its eigenbasis. And then you basically, try simplifying this. And when you try simplifying this, you get terms that look like this. So let me break this down for everyone. Over here, you have this factor that is 1 over the dimension of the K simplex space. And I mean the space of all K simplices, not just the ones that are actually there in our input graph. And then you basically have this expectation value over this gamma, which is basically this path of eigenvectors that's there in your path integral representation. So what I mean by that is if you look at this term W lambda, the W gamma, for instance, these all come from basically, again, inserting the resolutions of the identities and like combining, the inner products together. These are all inner products of eigenvectors associated to each of these one-sparse matrices. So these are all eigenvectors of the one-sparse matrices and the one-sparse decomposition. And this PR gamma over here is basically the probability. So the idea is you're basically summing over these. So for given a vertex, so you have think of some abstract vertex not related to the simplicial complex, but and this vertex has a degree of at most 2 to the R times 2 RD, which is basically the number of terms that are Trotter decomposition. And this inner product will only be 0 for a certain small number of other one-sparse matrices. So you're basically summing over these valid paths in your in this path interval. This is the implication over here. And the idea is that each edge in this path, if you were to depict this graphically, the set of valid paths in this graph is basically a graph where each vertex has a degree at most 2 to the R, 2 times R times D, and each edge corresponds to a path of connected eigenvectors for the one-sparse matrices that you use in this decomposition. And this probability is basically just telling you the probability of that happening. And so this averages the finite ensemble of random paths, and you want to select these with the Metropolis-Hastings algorithm. So the idea is you want a Markov chain, like the type basically like the undirected graph that I alluded to earlier. The idea is you draw the initial eigenstate of the first term as one-sparse decomposition, and then you transition to one of the 2 connected eigenstates. And the reason it's 2 is because you can prove mathematically that so one-sparse matrices, they have at most 2 non-zero eigenvectors, and so there's only at most 2 ways that these inner products over here in this W gamma term can overlap or be non-zero rather. And the probability of transitioning to one of the 2 connected eigenstates is basically proportional to this. So these are your transition probabilities for your Markov chain that you want to sample from using the Metropolis-Hastings algorithm. And you basically let it evolve to its stationary distribution. And then so you can show the number of operations that you need to sample from the distribution. That's that delta close to the stationary distribution is something like this, where R again is a number of terms in your Trotter decomposition, or number of time steps rather in your Trotter decomposition. D is the number of one-sparse terms that you have, And then gamma m over here is the spectral gap of the Markov chain. And then log 1 over delta is again the how close the distribution you're sampling on from is from the stationary distribution. So this whole procedure has multiple sources of error. There's the trotterization error. There's the error in estimating the dimension of the kernel from doing a finite time evolution, because remember we had to plug in t is approximately log 1 over epsilon over the spectral gap. And so this would not be an infinite time evolution. There's an error associated with that. There's an error, again, sampling from a distribution that's delta close to the stationary distribution of the Markov chain that I referred to in the previous slide. And there's also just the finite sampling error, and that you're drawing a finite number of samples. And there's also an additional source of contribution to the complexity, which is you need to draw a valid K-simplex at the start. And the idea is that this is basically proportional to the dimension of your K-simplex space, or the space of all K-simplices, over the number of K-simplices that are there in your input graph, or in the clique complex that's associated to your input graph. And so in order to actually draw a valid K-simplex, you need to draw a number of samples that's the inverse of this probability. And then you need to verify that each such sample is in fact a valid clique. And this basically scales as order the number of edges in your input graph. And so basically you can just query your oracle about this many times. And so if you combine all the errors and then you do the error analysis, you basically get this an expression like this for the total cost of this algorithm. Now it's not a great algorithm. I'm not claiming that by any means. However, the point is that there are certain conditions under which you can do this in polynomial time. And so this is polynomial scaling if this condition number, this kappa over here, is a condition number of the combinatorial Laplacian. And so basically if kappa and this d are polylogarithmic in the number of data points, then you have a hope of doing this in polynomial time. Another regime that this algorithm will be favorable in is if the graph is clique dense. Then this algorithm can be efficient. And there's also conjectures that the condition number of combinatorial Laplacian, it scales as a number of K-simplices to the 2 over d, where d is the dimension of your simplicial complex. And so if you use this naive bound for the number of K-simplices, which is basically 2 to the n, and if you plug in d equals n over here, you basically get something that approaches a constant for high dimensional simplicial complexes. So this conjecture, if true, is favorable to us. I should also point out that this exponential factor over here that might be concerning is coming from a very tight variance bound. I'm sorry, a very loose variance bound, a very, very loose variance bound. The condition number, so I already discussed how that would be bounded by. This D number over here, again, I mentioned earlier that this is basically it's basically proportional to like K, actually K squared. And then times the square of the maximum degree of your vertex in your input graph. And so those are not necessarily dependent on the number of data points. So this is still okay. And your K, for a given value of K, this is that value is fixed from the outset. So under these conditions, the point is that there are conditions under which you can do this classically in polynomial time. And this is a randomized classical algorithm. So let me stop there and ask if there are questions about this before I move on.
Any questions from the audience? I have a question. So
Yes.
these exponential terms, you mentioned, a bunch of error sources up at the top of the slide, right?
Mhm.
Are these exponential terms associated with one particular source of error?
You mean this one in particular?
Yeah, like both the epsilon exponent or the 2 to the, I was wondering if those were associated in particular with, say, the sampling error, or which one of these was the most kind of harmful, I guess, to the algorithm?
Right. So this is actually coming from a tight. So remember how there was like a Haar averaging that I was doing? So one of the contributions is basically Right, so that is associated with the finite, I think that's associated with either the Trot error or the finite sampling error. I actually should remember this. But it is definitely in one of these errors, and you can show that the error, the contribution to the error is basically the variance of that Haar averaging procedure. And this is again a very, very loose bound. So in most cases, or not most cases, but there are edge cases, for instance, when there's a lot of QuICs or a lot of simplices, or almost no simplices, where the variance is going to be much, much smaller than that. In which case, this algorithm would actually be much more favorable. And this algorithm, I should also add that there are some blowups that happen. Like, for instance, you would not want to use this in a very, you might think that, okay, based on this expression, this is really, really bad for graphs with not a large number of QuICs or k-simplices. And, but the other thing to keep in mind is that some of these terms don't, so a lot of this error analysis, a lot of these terms, like they're either very small or don't really contribute in those regimes. So you would not really use this expression to begin with. So this is more of an expression that's valid for like these intermediate regions. Yeah. And I should also add that this, again, is gamma m. This is the structural gap in the Markov chain. The only thing you know about this is that it's greater than 0, but less than or equal to 1. And unfortunately, this is the only parameter that's a bit of an unknown for this whole procedure.
Cool. And just maybe to mention for the audience, the QuIC, you know, when referring to a QuIC, that and a simplex are the same. Is that fair? QuICs and
Yeah,
simplex?
I'm mainly using this synonymously because the idea is if you're given an input graph which contains information about how the points are connected to each other, or how the vertices in the graph are connected to each other, you can create a simplicial complex out of that by saying that if you have a k QuIC in your graph, which is basically, so maybe I should have defined this earlier. So k QuIC, if you have a graph, a k QuIC is basically a collection of k points that it's a subset of the vertices. In this case, k, because it's a k QuIC, and such that each pair of vertices in that subset of points is connected by an edge. And so you would construct a simplicial complex out of this QuIC, or sorry, this graph, by basically associating a k simplex to a k plus 1 QuIC. If that makes sense. So
yes, k plus 1 because the number of points.
Yeah, that's right.
Gotcha.
Yeah. So this would be, so basically given the input graph, you basically form the QuIC complex on that graph, and then you go to determine the Betti numbers of that QuIC complex. And so, but you can, again, they can think of them as synonymous with the k simple or k plus 1 or k simplices. Yeah, the index convention here can be confusing, but and that's this term appearing over here. And yeah, so this again, this algorithm is not an amazing algorithm, and there's probably ways you can make tighter bounds on this, because yeah, the scales is like the 6th power of the condition number, the almost like d squared in the, or d to the 4th in the number of terms in the 1 sparse decomposition. So, but it is polynomial. Under there are sufficient conditions under which this can be done polynomially. And again, you can improve the variance bound depending on what, like significantly improve the variance bound depending on what you're doing, or depending on the data set you have. Are there any other questions?
I think we're good here in the audience, so you feel free to go on.
Right. So I just want to take this time, and now in the last portion of this talk, I just want to highlight some recent results. There's I think within the span of like a week or two, there was like a whole bunch of 4, 5, 6 papers on the TDA, doing quantum TDA on quantum computers, which generated some interesting memes on Twitter. So I should, before I get into some of these results, some of the more interesting results at least, I should point out that classically there are a few things that are known about the complexity of computing these Betti numbers. So the exact computation of the Betti numbers is generically NP hard, and it can actually even be p-space hard for certain types of topological spaces, namely what are known as algebraic varieties. So the question is like, what can be said about the complexity, the computational complexity of doing this on a quantum computer? And so a lot of these recent results are about that. So there's this one recent paper called QuIC Homology's QMA1 hard. So the idea is, again, if you have a QuIC complex and you want to determine the Betti numbers of that QuIC complex, they showed that determining the homology groups of those QuIC complexes is basically QMA1 hard. And it more generically is hard for arbitrary simplicial complexes. So they showed both of those things. And they and for those of you who don't know what QMA means, you can basically think of it as very loosely speaking, the class of decision problems whose solution can be verified by a quantum computer in polynomial time. So it's basically the quantum analog of NP. And if you actually want to count the number of the holes or whatever, the counting version of that problem is actually sharp BQP hard. So there's something about topology that, or actually, I should say this. What about approximations? Lloyd's algorithm that I discussed earlier in this talk, it shows that estimating normalized Betti numbers is in BQP under some conditions. The author Marcos over here, he actually proved earlier that it's DQC1 hard for general J complexes, and for those of you who don't know, DQC is a complexity class of problems solvable by a BQP machine, where you have a whole bunch of qubits, let's say n qubits, where one qubit is initialized in the 0 state and the remaining qubits are in the maximally mixed state. And there's a reason to believe that if something is DQC1 hard, then it's unlikely to be dequantizable. So there's still something quantum mechanical about this problem, despite the exact version of this problem being hard even for quantum computers to solve. And the way they went about proving this is actually quite interesting. They use techniques from not just topology, but also from supersymmetric many-body physics. They're basically considering certain types of supersymmetric Hamiltonians, and they basically show that some determining the properties of these Hamiltonians has direct implications for determining the topologies of simplicial complexes. And there's also another algorithm, another paper. Well, this is actually our paper. The algorithm that I was referencing is contained in this paper. We also developed a quantum algorithm, an efficient quantum algorithm for doing this, at least under some conditions. The scaling is something nasty. It looks well, not that nasty. It looks something like this. Again, you have like the number of QuICs. This is the Betti numbers. R is the absolute accuracy. R is the relative accuracy to which you want to determine the Betti numbers. And then E is like the number of edges in your input QuIC complex. And then lambda min is the spectral gap. So the speed up, as you can see, just based on like the presence of these factors, especially this one, the speed up is large, so we have a speed up when the Betti number is large, and the spectral gap is not too small, because this factor is the basically looking at what factors in the denominator of this cost. And it can also show that if you're only concerned with eigenvalues below a certain threshold, you can modify this algorithm to basically give an algorithm for estimating Betti numbers in this cost, which is more a bit more favorable. So the question is, okay, are there examples of spaces with large Betti numbers? What can you say about the spectral gap and about these Betti numbers? And this is also relevant to our algorithm because our randomized algorithm also benefits from QuIC dense regimes and also spaces with the large Betti numbers. So there's a generic type of QuIC, the graphs called K-partite complete graphs, which are basically, so here's an example of a K-partite complete graph. The notation here is K5,6 because there are 6 partitions and each partition contains 5 vertices. So that's a notation. And these types of graphs are called K-partite complete graphs. And there's also certain types of graphs called Erdos-Renyi graphs. And so if you take the QuIC complexes of these 2 graphs, they have large Betti numbers. And then so for RIPS complexes, it turns out that there's a result that's been shown that if you take the Betti number, the kth Betti number of a RIPS complex, then And if you divide by, n to the k, where n is the number of data points that you have, this basically approaches 0. So the idea is it does not grow polynomially in the number of data points. That's what this is saying. Generically, that does not happen. Now, there are certain examples that we were able to construct in our paper where your RIPS complexes do have large Betty numbers. And so this is an example of one such complex. But this is kind of like a very contrived example. So when we say that these are efficient quantum algorithms, there are some qualifiers that need to be made there. So if you're interested in any of this, please feel free to check out this paper. And then lastly, I should also point out there was a follow-up paper by Seth Lloyd and a company where they talk about the complexity theoretic limitations on TDA. And they basically walk back on some of the more egregious claims that they made in their 2016 paper. And they basically show that the quantum algorithms for TDA run in exponential time for almost all inputs. And so more specifically, they showed that computing Betty numbers is sharp P hard. And while the problem of approximating the Betty numbers is actually NP hard generically. And they also showed that both problems, they retain their hardness if we're just restricted to the regime where quantum algorithms are thought to perform TDA best, namely these QuIC dense regimes. And they actually revisit the algorithm that I presented earlier in this paper, in this presentation, and they show that it actually at best achieves a quadratic speedup on average, and maybe like quartic in best case. So it's not really like an exponential speedup as initially thought. However, they do argue that if you were to, as part of your input model, you were to input the data as like a specification of simplices rather than like an input graph or a list of vertices or data points, then you actually can recover an exponential advantage. So these are some interesting complexity theoretic implications of this recent work. So the conclusion is that TDA generically provides a rich set of problems in which to investigate potential quantum speedups. There are still a few open problems left. You can show that while it's been shown that it's a hard problem when you consider the exact Betty numbers, it's still actually unknown if it's hard when you consider combinatorial Laplacians. And this is related to the fact that it's been shown that estimating the low-lying states of the spectral density is for arbitrary Hamiltonians is DQC1 hard. But again, that doesn't necessarily mean that that's true for every single example of a Hermitian matrix. So it's actually unknown if that's still hard if you consider these combinatorial Laplacians, which are sparse matrices. And it's actually also unknown if estimating normalized Betty numbers is DQC1 hard for specifically QuIC complexes. So that's an open question. And there could very well be some advantages there, depending on how you can reconcile this with Seth Lloyd's results. And there are deep connections, and I guess the other message of this talk is that there are deep connections between topology, many-body physics, and complexity theory that are worth exploring, that make this area worth exploring and investigating. And so stay tuned for further developments. Thank you.
All right. Thank you, Abishek.
Yeah, thank you. Are there any questions? Sorry, I went through the last part rather quickly. But
we are a little over time, so I understand if people have to leave. Otherwise, let's feel free to stick around. And yeah, are there any questions from the audience? So I guess it essentially sounds like there's some, it very much depends on the context, like the input model of your data, whether it's a graph or given to you actually as the complex. So maybe, I don't know, more of a comment, but looking for like a final answer as to whether this problem is sort of able to provide quantum advantage or not seems very context dependent. Would you agree?
Oh, absolutely. Yeah. If I mean, I haven't been able to look at like Seth Lloyd's paper over here in detail, but yeah, the fact that they say the fact that they show or argue that you can get an exponential advantage if you have an oracle that gives you the simplices directly, then yeah, that is I guess that's not that surprising, but yeah, it is still interesting. And there's things that are, I mean, I would still say that there is something, the fact that some of these problems are DQC1 hard, and are probably immune to therefore immune to dequantization. There is something that's quantum mechanical about TDA, and in fact, you can show that a lot of these Laplacians and boundary operators, you can actually think of them as fermionic operators. If you want to take the sort of like physics kind of approach to the thinking about these things. So it's not surprising that, for instance, in our path integral approach, we weren't able to get like a super efficient algorithm, because that's essentially the sign problem, right? You have at that point if you wanted to estimate do like imaginary time revolution on the combinatorial Laplacian. So there is, I would still say there is something quantum mechanical about the problem, but it is not just like a blanket, oh, like quantum computers can provide an exponential speed up for this problem generically. So yeah, you're absolutely right.
Okay.